Hi everyone, my name is Tome Eftimov, and today I'm going to present our work portfolio selection for automated algorithm selection in black box optimization. This work is done in a collaboration between three institutions: the Jožef Stefan Institute, the Leiden University, and the Sorbonne University. You can see like the list of all authors. It was fun collaborating on this topic, and this is like the outcome of our topic. So what we are actually addressing here is the algorithm selection in numerical black box optimization. And the main goal of an algorithm selection is to find like the best algorithm which is suitable for a given problem instance that is needed to be solved. So for this purpose, we need to have like a set of problem instances for which we want to find the best algorithm, and the set of problem instances are creating the problem portfolio. We need to have a set of algorithm instances which are creating the algorithm portfolio, and these are the algorithms for which we can choose. And once we have the problem portfolio and the algorithm portfolio, nowadays, like one of the most commonly used approaches to apply some supervised machine learning task. For example, we can do like regression, classification, pairwise regression with different kinds of machine learning methods, and then to learn the algorithm selector. A recent study actually shows that there is no significant difference in performance of different machine learning methods and different algorithm selection approaches, which actually are related to the learning task in the scenario of the black box optimization. And we need to take care here that this result is coming based on the BBOB data which is available in the community. So the two questions that remain open is actually which problems to be included in the problem portfolio, and also which algorithms to be incorporated in the algorithm portfolio, because they can have like really big effect on the performance of the algorithm selector. In this study, we are actually addressing the second question, and we want to find a way how we can find which algorithm to be involved in the algorithm portfolio, because current practices are actually based on some greedy selection, which means that we are selecting the algorithms that perform well based on some similar reference task, or looking in some benchmark empirical data, or using some domain knowledge, and then we are selecting the algorithms that are included in the algorithm portfolio. What we want to do in this study is actually, can we select the algorithm portfolio by using some data-driven approaches, or can we automate this process? Our approach consists of two steps. The first one is we learn like a meta representation that represent like algorithm performances on problem instances. For this purpose, we investigated two meta representations: the performance to vec, which are vector of algorithm performances on all instances from the problem portfolio, and the shape meta representation, which is indirect outcome of explainable algorithm performance prediction. In each algorithm is represented as a vector of shapely values averaged across like all instances from the test set, and further across different poles depending from the evaluation of the machine learning algorithm that is used for automated algorithm performance prediction. So no matter which meta representation is actually used, what is the next step is to apply a sampling heuristic that is able to select diverse, representative, and non-redundant algorithms using this meta representation. For this purpose, we apply the selector, where the idea is like we generate a graph of algorithms. Each algorithm is a node, and they are connected with an edge. If the cosine similarity of their meta representation exists a certain threshold. So once we have the graph, we apply like two different algorithms from graph theory: the maximal independent sets and dominating sets, which are able to extract only diverse, representative, and non-redundant nodes. So in our case, these are algorithms. And what is really important to mention is like that both of these graph algorithms are stochastic in nature, so we need to repeat them like the selection with differences in order to guarantee about robustness. So this is actually how this looks like. To have like better insights about this, what we are doing, we are creating the graph, then we are applying based on some meta representation. Top here you can see, for example, the shapely. In the bottom of this figure, the performance to vec. And then with different thresholds, the graphs are created with different similarity thresholds. And then we are selecting the algorithm. For example, the blue nodes are selected, the green nodes are not selected. However, what is really important is that all this investigated, the both investigated meta representation, the performance to vec, and the shapely meta representation provide us diverse algorithm based on overall performance. But sometimes we want to have like complementarity not based on overall performance, but we want to have complementarity on a problem level. And this is the reason why actually we develop a special case which we call personalized shape meta representation, which are a synergy between the data-driven and greedy approaches. So what we have done here is actually we use the shapely values on a local level, on a problem level, And we create this meta representation and use this meta representation to create a graph for each problem separately. Then we run the selector as a sampling heuristic several times. Then we use the union of the return algorithms like the nodes which are non-redundant, representative, and diverse. And then further from the union for each problem of union of all return algorithms, we select the two best performing algorithms based on raw performance data, from which it comes like that this is a synergy between the data-driven and also a greedy selection. We are not going to in more detail about the experimental setup, but we use 120 problem instances from DBOB, 324 modular CMA evolutionary strategy configurations, and then in case to build like a shapely meta representation, we use a random forest. So we investigated single target regression models. We have like one for each configuration, and further we use the shapely explainability method to find like this shapely meta representation once each single target regression model was trained. Again, like when we have the building and evaluating the algorithm selector is a common scenario in all other studies which are dealing with the algorithm selector. We are interested in the loss between like the selected solver based on the algorithm selector and the virtual best solver from the which is the best performing algorithm for that particular problem. However, because we are generating new algorithm portfolios, we want to baseline the algorithm selector performance with different baseline algorithm portfolios, which in our case are like the full portfolio, all 324 configuration, the greedy portfolio in which we involve like 10 best performing algorithm based on any time performance, and then we have the greedy portfolio, which is per function, and these are actually for each problem instance, we select the two best performing algorithm for each pair of problem dimension, and actually budget the function evaluation where the algorithm the function evaluation, which is like the stopping criteria where actually we are measuring the performance of the algorithms. Here you can see some insights about like how these the portfolios are generated with different meta representation we investigated. We can see like that the performance to web-based approach is portfolios which are smaller in size than those generated via shape meta representation. But this was an expected outcome. Why? Because the performance to web encodes algorithm performance only using high-level information, while shape capture diversity on a lower level, taking into account problem landscape characteristics. So performance to web favors smaller portfolios, while shape meta representation, they have like much larger portfolios from which we can select. When we use these portfolios and also the baseline portfolios, and we use the algorithm selector to train them, we got like these total losses. So here in this heat map, we can see like the results of training an algorithm selector with all these algorithm portfolios for 5-dimensional problems, 30-dimensional problems, and also different budgets, which are actually the roles of the heat maps. What we can see on this heat map is actually that the positive values are better, which means that the algorithm selector with our selected subset of algorithms provide better results than the algorithm selected used with the full portfolio. What we also need to mention here, these are actually the results which are averaged across all problem instances and then average across different algorithm portfolios that are results from different sampling seeds, So what we can see here is actually that for 5D, the personalized portfolios actually outperform the full portfolio, and they are comparable with both greedy approaches, overall performance and per function. In 30D, like the personalized portfolios outperform like the full portfolio, and also they outperform the both greedy selection, both greedy baselines. When we look at the performance to WAC, they actually yields performance to WAC yield to the worst result, and we can see that still there are some positive insights when we look at 5D and small function evaluation, for example, 500 evaluations. And the shape-based portfolio leads to overall better performance for large budgets than the full, greedy overall, and the greedy per function. So what in overall, we can see that the shape-based portfolio seems to slightly outperform the performance to WAC-based portfolios which are generated. However, because we always said, we have already said that the performance to WAC favors smaller portfolio, and we have smaller portfolio, there is no guarantee that the best performing configuration will be included in the portfolio. And on the other side, Shapely favor like larger portfolios. There is like much more flexibility to algorithm selector to select the configuration, and with this we have like the error of making the true selections actually increases. For this purpose, to see what is happening, we want to find like portfolios that are still better than the pooled portfolio, but they have like this inner loss, which is smaller than the greedy, the greedy minus the outer loss. So what we have done here we have the 5D and budget of 2000 function evaluation. We decompose the total error. On x-axis, we have the difference between the portfolio virtual best solver and the virtual best solver of the full set of 324 algorithms. So we can measure if the best performing algorithm is actually included in the portfolio. And on epsilon axis, we have the difference in performance between the algorithm it selects and the virtual best solver of the portfolio it can choose from. So actually within the same portfolio that is selected by our approach. What we can see here is that several performance to back and Shapley based portfolios lead to lowest total loss. Also, some performance to back and Shapley portfolios lead to better results than greedy. And overall, and greedy per function baseline, both personalized portfolios lead to better results than the other function. And if we compare with the full portfolio is a diagonal line that goes through 2 on x and epsilon axis. So similar patterns are actually visible on different combinations between dimensionality of the problems and also the budget for which we are evaluating the algorithm selector. So what we can see, conclude, like based on our study, is that actually we can automate the step of selecting diverse and complementary algorithms. When we focus like on different the portfolios we actually selected based on different representations, we can see that the performance to back are smaller. They can lead to high performance case in the algorithm selector, but they have low flexibility, while the shape-based portfolios, they are larger portfolios, they have high flexibility, often contain the best performing algorithm for each problem instances, but then we have like low performance case because the algorithm selection task is actually much more complex task, and the error of making the true selection can increase. What is actually the really positive outcome is that these shape-based portfolios are competitive with the greedy selection, which means that our question, which can we automate this approach, actually leads to good results. So for future work, we are planning to extend like our approach to other modular frameworks, also including portfolios with algorithms from different algorithm classes. And instead of using like some meta features that describe the landscape characteristics and also linking them to the performance that is achieved by some machine learning method, we are also planning to investigate some trajectory-based meta representation that capture the algorithm behavior during the optimization run on a particular problem. Thank you for your attention. If you have some questions, feel free to ping all authors. We will be happy to discuss on this topic. Thank you again.